Somewhere above you tonight, whether you can see it or not, there is a star close enough to be called our neighbor, Proxima Centauri, and if you sent a message toward it right now, it would still be traveling 4 years from now. Not arriving, still traveling. 4 years and 3 months, one way, at the fastest speed anything is allowed to move. Here's the strange part. That speed limit was never really a limit on speed. It was a limit on motion through space. Space itself was never bound by that rule at all. If you love deep space and the edges of real physics, take a second to like this video and subscribe to Blackout Universe. It helps this channel reach more people who think about these things the way you do. Get yourself comfortable. Let's begin. 4 years and 3 months. That is how long it would take a beam of light, the fastest thing that exists, to cross the gap between our sun and the next nearest star. Proxima Centauri sits 4.24 light-years from where you are sitting right now. In miles, that number becomes almost meaningless, about 25 trillion of them. But the distance itself is not really the problem. The problem is what that distance does to everything we have ever built to cross it. Our fastest achievement so far is a small metal probe called Voyager 1, launched in 1977. Nearly 50 years later, it remains the most distant human-made object in existence, moving at roughly 38,000 miles per hour, faster than almost anything else we have ever sent into space. And if Voyager 1 were somehow pointed directly at Proxima Centauri, which it is not, the trip would take about 73,000 years. 73,000 years to reach the very nearest star. Not the edge of the galaxy, not some far-flung cluster on the other side of the Milky Way, the next one over. Here's what that number is quietly asking you to accept. Nearest, in the language of the universe, still means further away than the entire span of recorded human civilization, several times over. Agriculture is about 12,000 years old. Writing is about 5,000 years old. 73,000 years is longer than the time since the last ice age began to end. That is the scale of the gap to the closest neighboring sun. Not the furthest, the closest. And Proxima Centauri, in cosmic terms, is next door. Our galaxy, the Milky Way, is about 100,000 light-years across, holding somewhere between 100 and 400 billion stars. To leave it entirely and reach the next galaxy over, Andromeda, would mean crossing about 2.5 million light-years. The observable universe, the total volume of space we can detect in any direction from Earth, stretches roughly 93 billion light-years across. These are not numbers built to be understood the way you understand the walk from your house to the corner store. The human mind evolved to judge distances across a plain, a valley, a coastline, not across a void that swallows tens of thousands of years the way a hallway swallows footsteps. Notice something. If the fastest thing our species has ever built takes 73 millennia to reach our closest stellar neighbor, then under our current capabilities, the universe is not simply large, it is closed. Every star you can see with your eyes on a clear night sits behind a wall built not of steel or stone, but of pure distance. No engine we currently possess has any real chance of getting through it in a human lifetime, or 100 human lifetimes. For most of scientific history, that would have been the entire story. A universe too vast to visit, a species confined by simple arithmetic to one small planet, orbiting one ordinary star. But arithmetic is not physics. There is a difference between a wall built by engineering, which can eventually be solved with better engines, and a wall built by the fundamental laws of the universe itself, which cannot be solved by effort alone. To understand which kind of wall we are actually facing, we have to go back to the moment that wall was first discovered. Not assumed, not guessed at, proven, in the early 20th century by a young physicist working a desk job in Switzerland, trying to make sense of a much stranger question than how far away the stars might be. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would eventually rewrite the rules of space and time themselves. His name was Albert Einstein. At the time, he held no university position. He was not running a laboratory. He was examining patent applications for a living, doing physics on the side, in the hours before and after his shift. The paper he wrote that year carried the title, On the Electrodynamics of Moving Bodies. Today we call the theory inside it special relativity, and it began not with a bold claim about the universe, but with a strange, stubborn little fact that refused to behave the way everything else in physics behaved. Start with something ordinary. Picture standing at the side of a road as a truck drives past at 60 miles an hour, and someone in the truck bed throws a ball forward at 20 miles an hour. From where you stand, that ball is not moving at 20 miles an hour. It is moving at 80, because the truck's speed and the ball's speed simply add together. This is not a special insight. It is common sense, confirmed by nearly every physical experience a person has ever had. Velocities add. That is how the world works. Except physicists in the late 1800s had already discovered that light refused to follow this rule, and the discovery unsettled them badly. Physicists at the time assumed light needed something to travel through, the way sound needs air, a medium they called the ether. If Earth were moving through this ether, as it orbited the sun, light should travel measurably faster in one direction than another, the same way a sound wave moves faster with the wind than against it. Two American scientists, Albert Michelson and Edward Morley, built an extraordinarily sensitive instrument in Cleveland to catch that difference. They found nothing. No matter which direction they measured, in which season, at which time of day, light moved at exactly the same speed. For years, physicists tried to explain the result away as some flaw in the apparatus, some hidden effect they had not accounted for. Nobody wanted to believe it. The instrument was too precise, the result too clean, and too strange. Einstein's paper took that stubborn, unwelcome result and did something almost nobody else was willing to do. He accepted it completely, at face value, and asked what would have to be true about the universe for that result to make sense. His answer was radical. The speed of light, roughly 186,000 miles per second, does not change depending on how fast you or the light source happen to be moving. It stays fixed, for every observer, everywhere, always. If you are standing still and someone flies past you at half the speed of light while shining a flashlight forward, you do not see that light moving at 1.5 times its normal speed. You see it moving at exactly the same 186,000 miles per second you would measure from anywhere else. Not faster. Not slower, the same. Return to the truck for a moment, but now push it to half the speed of light, and swap the ball for a flashlight switched on and pointed forward. Common sense says the light should race away at 1.5 times its usual speed. Einstein's mathematics said otherwise. And nature, tested again and again in the decades since, has agreed with Einstein every single time. the light still moves at exactly the same fixed speed, regardless of the motion of the truck or the flashlight or you. That's strange enough to sit with for a moment. A universe where speeds refuse to simply add together, where one number in all of physics holds perfectly still, no matter how fast everything around it moves. This single, small, stubborn fact, the constancy of the speed of light, was not itself the theory, it was the seed. Once Einstein accepted it as true, he had to explain how it could possibly be true, and the explanation forced him to abandon something physicists had assumed, without question, for over 200 years. Space and time were not fixed backgrounds against which motion happened. They were flexible, they bent. And once space and time themselves were allowed to bend, an entirely new kind of speed limit came into view, not one built by engineers, one built into the architecture of reality itself. The next part of the story is about exactly how far that bending goes, and how we know with absolute certainty that it is real. If the speed of light refuses to change, something else in the equation has to give. That was the puzzle Einstein faced in 1905, and his answer was almost unthinkable at the time. Space and time themselves would have to flex, not as an illusion, not as some trick of perception, but as a real, measurable feature of the universe. This produces two connected effects, and both are strange enough that they seemed, for decades, more like a thought experiment than a description of reality. The first is time dilation. Time, for someone moving very fast relative to you, passes more slowly than it does for you. Not because their watch is broken, not because they feel anything different. From your perspective, watching them, their clock genuinely ticks slower. The second is length contraction. Distances, measured in the direction of motion, physically shrink for someone moving close to the speed of light, compared to how those same distances appear to someone standing still. Neither of these is a metaphor. Both have been tested, and both have held up every single time. Here's where the numbers start to escalate quickly. At 50% of light speed, time runs about 15% slower for the traveler, compared to someone at rest. At 90%, it slows by more than half. At 99%, roughly 7 times slower. At 99.9%, by a factor of about 22. At 99.99%, by a factor of roughly 70. The closer you push toward light speed, the more violently time dilation accelerates, curving toward infinity as you approach that final, unreachable line. What that means, in practice, is a traveler moving fast enough could experience a journey that feels, to them, like a matter of years, while decades or centuries pass for everyone they left behind. This is not speculation. It has been measured directly, repeatedly, in systems most people rely on every single day. GPS satellites orbit Earth at roughly 8,700 miles per hour, and due to their speed, their onboard clocks run measurably slower than clocks on the ground, by about 7 microseconds per day from velocity alone. At the same time, because they sit farther from Earth's gravity, a separate effect from general relativity speeds their clocks up by about 45 microseconds per day. The net result, GPS satellite clocks run about 38 microseconds per day faster than clocks on Earth's surface, and engineers must correct for this difference constantly. If they did not, GPS positioning would drift by about 6 miles a day, and every map, every navigation system, every emergency dispatch relying on GPS would slowly become useless. Every time your phone finds your location, it is quietly agreeing with Einstein. There is a second, independent confirmation, this one written across the sky itself. Muons are subatomic particles created when cosmic rays strike the upper atmosphere, roughly 9 to 12 miles above Earth's surface. Muons decay extremely fast, with an average lifespan of about 2.2 microseconds. At that lifespan, even moving near the speed of light, a muon should only travel about 2,000 feet before disintegrating, nowhere near enough distance to reach the ground. And yet, muons are detected at sea level in large numbers every day. The explanation is time dilation. From our perspective on the ground, the muon's internal clock runs so slowly, moving at such extreme speed, that its short lifespan stretches long enough for it to survive the full descent. The particle's own experience of time and our experience of its journey no longer match. The mismatch is exactly what Einstein's mathematics predicted more than a century ago. So time dilation and length contraction are not theoretical curiosities. They are measured, verified, load-bearing parts of modern technology and modern physics, and they answer part of the question this video opened with. Light's speed stays fixed because everything else around it, time and distance, bends instead. But bending time is only half the story. There is a second cost to approaching light speed, one that does not just distort your experience of the journey, but actively prevents you from finishing it at all. That cost is written in a single, brutal equation. Time bending is strange, but survivable. What comes next is not. As an object moves faster and faster, approaching the speed of light, something happens to how much energy is required to push it further. This is where Einstein's most famous equation stops being a slogan printed on posters and starts being the reason interstellar travel, using any propulsion method we currently understand, runs into a wall that cannot be engineered around. The equation is E equals mc squared. Energy equals mass times the speed of light squared. Most people know the formula without knowing what it actually forbids. As an object accelerates and gains kinetic energy, that energy behaves, in a real physical sense, like additional mass. The object does not literally get heavier, the way a suitcase gets heavier when you pack more into it. But from the perspective of anyone trying to accelerate it further, it takes more and more energy to produce the same increase in speed, exactly as if the object had become more massive, and the closer that object gets to light speed, the worse this effect becomes. Here's what that looks like in real terms. Accelerating an object from rest to 50% of light speed takes a certain calculable amount of energy. Accelerating that same object from 50% to 90% takes dramatically more energy than the first jump, even though the increase in speed, in absolute terms, is smaller. From 90% to 99%, more energy still. And from 99% to 99.9%, a gain of less than 1 percentage point, the energy required dwarfs everything that came before. As you approach light speed, the energy curve does not rise steadily. It curves upward, almost vertically, climbing toward infinity as your speed approaches, but never quite reaches that final number. Reaching exactly the speed of light would require infinite energy, and infinite energy does not exist anywhere in the universe, available to any civilization at any level of technology. This is not a limitation of current rocket engines. It is not something better fuel or a bigger ship could eventually solve. It is a mathematical wall, built into the relationship between mass, energy, and velocity, and no amount of cleverness changes the equation. Light itself can travel at light speed only because photons, the particles of light, have no mass to begin with. Anything with mass, a spacecraft, an astronaut, a single atom of hydrogen, faces a cost that becomes literally unpayable as it nears that line. That's why, even using our most optimistic current propulsion concepts, reaching even a small fraction of light speed with a crewed spacecraft remains, for now, entirely out of reach. The fastest human-made object in history is the Parker Solar Probe, launched by NASA in 2018, which at its closest approach to the Sun reaches speeds of about 430,000 miles per hour, using the Sun's own gravity as a slingshot. That sounds extraordinary, and it is, by the standards of anything humans have built. And yet 430,000 miles per hour is still only about 0.064% of the speed of light. At that speed, reaching Proxima Centauri would still take over 6,600 years. Our fastest object, built using the most advanced techniques available today, is still nowhere near the range where relativistic mass becomes a serious obstacle. We are not close enough to the wall to have hit it. We simply do not yet have an engine capable of getting near enough to test it directly with a spacecraft. But we have tested it, not with spacecraft and not with astronauts, but with something far smaller, far faster, and far easier to observe. For decades, physicists have been accelerating particles to speeds approaching light itself, inside machines built specifically to probe the outer edge of what physics allows. And every single time, without exception, the same wall appears. What those experiments reveal is not a theory anymore. It is a confirmed, repeated, thoroughly tested limit. The next part of this story takes us inside the machine, where that limit gets demonstrated, over and over, 11,000 times every second. Beneath the border of France and Switzerland, roughly 300 feet underground, sits a ring of superconducting magnets, 17 miles in circumference. This is the Large Hadron Collider, built by CERN, the European Organization for Nuclear Research, and switched on for its first full operation in 2010. Its purpose is to accelerate particles, mostly protons, to speeds close enough to light that physicists can study what happens when matter is pushed to the very edge of what the universe allows. And what the Large Hadron Collider has demonstrated, again and again, for well over a decade, is the mass wall in direct, repeatable action. Inside the collider, protons are accelerated until they reach roughly 99.9999991% of the speed of light. At that velocity, a proton circles the entire 17-mile ring more than 11,000 times every single second. In the time it takes you to blink, a proton inside that machine has already circled the ring several thousand times. These are not modest speeds. They are about as close to light speed as anything with mass has ever been deliberately pushed. And yet, no matter how much additional energy engineers pump into the system, the protons never cross that final threshold. They get closer. The decimal places extend further, more nines added after the point, but 100% never arrives. This is not a limitation of CERN's equipment, and it is not for lack of trying. The Large Hadron Collider represents one of the largest, most expensive scientific instruments ever built, constructed specifically to push particles as close to the light barrier as engineering allows. Its own operating budget runs into the billions of dollars, funded by dozens of countries, staffed by thousands of physicists and engineers. If more energy could simply buy the final percentage point, someone would have already spent it. Here's the shape of the problem. Physicists sometimes describe this as an asymptotic curve, a term borrowed from geometry describing a line that gets infinitely close to a boundary without ever touching it. Picture walking toward a wall, where with every step, you cover only half the remaining distance. First you cross half the room, then half of what remains, then half of that. You keep getting closer, forever, without ever technically arriving. The Large Hadron Collider's protons behave exactly this way. Each additional burst of energy buys a smaller and smaller sliver of additional speed, an ever-diminishing return, stretching out toward a target that recedes precisely in proportion to how hard you push toward it. The light barrier is not a theoretical ceiling that might someday be revised as our instruments improve. It has already been tested at extraordinarily high precision under controlled laboratory conditions, using some of the most sensitive measurement equipment humanity has ever built. Every particle physics experiment conducted since the mass-energy relationship was first confirmed in the early 20th century has returned the same result. The speed of light, for anything with mass, is not just difficult to reach. It is unreachable by the very architecture of the universe those particles exist inside. This is where the story could simply end. A wall, discovered mathematically in 1905, confirmed experimentally thousands of times since, holding firm under every test physicists have thrown at it for over a century. Interstellar travel, at least by any conventional means, closed off permanently by the deepest laws of physics we know. For most of the 20th century, that conclusion was treated as close to final. But there is a detail buried inside Einstein's own equations, one that took another decade after 1905 for Einstein himself to fully work out, and that detail does not break the light barrier. It does something stranger. It reveals that the barrier was never quite as absolute as it first appeared, because the rule it protects was never really a rule about speed at all. 10 years after his 1905 paper on special relativity, Einstein published a second, far more complex theory, one that would take him nearly a decade of difficult mathematics to complete. In 1915, he presented general relativity, a theory that did something special relativity had never attempted. It described gravity not as a force pulling objects toward one another, but as the curvature of space and time itself, bent by the presence of mass and energy. A planet does not orbit a star because the star is reaching out and pulling it. A planet orbits because the star has curved the space around it, and the planet is simply following the straightest possible path through that curved space. It is a strange, almost architectural way of thinking about gravity, and it turned out to be extraordinarily accurate, confirmed by observation after observation in the century since. But general relativity carried a second implication, one that took physicists years to fully appreciate. If space itself could bend under the influence of mass, then space was not a fixed, passive backdrop. It was something closer to a physical substance in its own right, one that could stretch, curve, compress, and, crucially, expand. And nowhere in Einstein's equations, either the 1905 version or the 1915 version, is there any statement that space itself is limited to the speed of light. The speed limit special relativity describes applies to objects moving through space. It says nothing at all about how fast space itself is allowed to move, stretch, or expand. Here's the distinction that changes everything, and it's worth restating clearly, because it is easy to miss the first time you hear it. An object with mass, a spacecraft, a planet, a person, cannot move through space faster than light. That rule remains completely intact, untouched, exactly as confirmed by a century of Large Hadron Collider experiments. But space itself is not an object. It is the medium, the stage, the fabric that objects move through, and the fabric itself was never bound by the same rule as the actors moving across it. Picture an ant standing still on the surface of a balloon. The ant, relative to the balloon's surface, is not moving at all. But if you inflate the balloon rapidly, 2 points on its surface can move apart from each other extremely quickly, even though neither point, and certainly not the ant, is doing any walking. The distance between them is growing because the surface itself is stretching, not because anything is crossing that surface. No analogy fully captures the geometry of the universe, but this one captures the essential distinction physicists are pointing to. Motion through a medium and the expansion of the medium itself are two entirely different kinds of motion, governed by two entirely different rules. This distinction is not a fringe interpretation or a loophole discovered by searching for one. It falls directly out of the mathematics of general relativity, a theory tested with extraordinary precision for over 100 years, confirmed by the bending of starlight during the 1919 solar eclipse expedition led by Arthur Eddington, confirmed again by the existence of gravitational waves, first directly detected in 2015 by the LIGO Observatory, confirmed by the everyday accuracy of the GPS correction discussed earlier in this video. General relativity is not a shaky or speculative theory. It is one of the most rigorously tested frameworks in the history of science, and it is this same, thoroughly confirmed theory that contains, quietly within its own structure, a distinction that light speed applies to motion through space, but not to space in motion itself. If that distinction is real, and the mathematics says it is, a question follows almost immediately, one that sounds, at first, like it belongs in science fiction rather than a physics journal. If space itself can expand without limit, is there anywhere in the observable universe where we can actually see that happening? Is there proof, not theoretical, not hypothetical, but observed, that space itself moves faster than light? There is, and it is happening right now, in every direction you could possibly look, far out at the edges of everything we can detect. In 1929, an American astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made an observation that would permanently change how we understand the universe. Studying distant galaxies, Hubble noticed something strange in their light. The light arriving from nearly every galaxy he measured was shifted toward the red end of the spectrum, a phenomenon called redshift, and the amount of that shift was not random. It was proportional to distance. The farther away a galaxy sat, the more its light had stretched, and the faster that galaxy appeared to be moving away from us. This relationship became known as Hubble's law, and it remains one of the foundational observations of modern cosmology. The explanation, confirmed and refined over the decades since, is that the universe itself is expanding. Space, in every direction, is stretching, carrying galaxies apart from one another as it grows. This is not galaxies flying outward through fixed space, the way debris scatters from an explosion. It is the space between galaxies increasing, continuously, everywhere, all at once. Return to the balloon for a moment, but paint dozens of dots across its surface, representing galaxies. As the balloon inflates, every dot moves away from every other dot. Not because any dot is walking anywhere, but because the surface connecting them is stretching in every direction simultaneously. No dot is the center. Every dot sees every other dot receding. Hubble's law comes with a precise number attached to it, refined many times since 1929 through increasingly accurate observations. Current measurements place the rate of cosmic expansion at approximately 70 kilometers per second for every megaparsec of distance, a megaparsec being about 3.26 million light-years. Here's what that means. The further away a galaxy sits, the faster the space between us and it is stretching. And because that rate of increase compounds with distance, there comes a point, calculable and specific, where a galaxy sits far enough away that the space between us and it is expanding faster than light itself. This is not a hypothetical boundary. It is called the Hubble volume, and galaxies beyond its edge are, right now, receding from us faster than light can travel. To be clear about what this does and does not mean, because the distinction matters enormously, those galaxies are not moving through space faster than light. Nothing inside them is violating the speed limit confirmed at the Large Hadron Collider. The space between us and them is simply expanding fast enough that the total distance grows faster than light can close it. Light emitted from those galaxies today will never reach Earth. Not because the light is too slow, because the distance is growing faster than the light can cross it forever, receding into a gap that only widens with time. Notice what this confirms. The theoretical distinction drawn from Einstein's equations, that space itself carries no speed limit, while objects within it remain bound by one, is not simply permitted by the mathematics. It is observed, continuously, as a defining feature of the universe we actually live in. Every galaxy beyond the Hubble volume stands as a kind of natural proof that the loophole is real. Space itself moves, and when it moves, light speed simply does not apply to it. This raises the question that turns a cosmological curiosity into an engineering proposal, however speculative. If the natural expansion of space can already carry galaxies away from each other, faster than light, without violating a single law of physics, could that same behavior, in principle, be engineered? Not on the scale of galaxies, but on the scale of a spacecraft. Could space be made to expand behind a ship and contract in front of it, deliberately, used as a kind of current to ride rather than an engine to fight against? For decades, this question sat mostly unexplored, a strange implication of general relativity that nobody had bothered to formalize into an actual proposal. Then, in 1994, a physicist working in Wales did exactly that, publishing a paper with an equation so unexpected that physicists are still arguing about its consequences today. In 1994, a physicist named Miguel Alcubierre, working at the Department of Physics and Astronomy at the University of Wales in Cardiff, published a short paper in the journal Classical and Quantum Gravity. The paper was only a few pages long, but it did something no serious physicist had managed to do before. It described a way to travel faster than light without breaking Einstein's equations, not around them, not by ignoring them, using them directly, exactly as written. Alcubierre's insight came from taking the distinction from the previous section, the one between motion through space and the expansion of space itself, and asking a very specific engineering question. If galaxies at the edge of the observable universe can recede from us faster than light, simply because the space between us is expanding, could that same mechanism be shaped deliberately, on a much smaller scale, around a single spacecraft? Could you build, mathematically speaking, a localized bubble of space that expands behind a ship and contracts in front of it, using the motion of space itself to carry the ship along, the same way the current of a river carries a boat, rather than the boat's own engine. The mathematics said yes. Alcubierre worked out a solution to Einstein's field equations, the core equations of general relativity that described exactly this kind of bubble. Behind the ship, space would stretch outward. In front of the ship, space would contract inward. The ship itself would sit inside a small, flat region of ordinary space-time. At the center of the bubble, neither expanding nor contracting, simply being carried forward as the space around it reshaped itself. And because the ship, from the perspective of anyone inside that bubble, is not moving through space at all, it is not actually violating the light speed limit. It is being carried by a wave of geometry, the same way a surfer is carried by an ocean wave without personally generating the wave's speed. To an outside observer, watching the ship cross vast distances in a short time, it would appear to be moving faster than light. But locally, inside its own patch of space, it would not be moving at superluminal speed at all. Both statements are true simultaneously. Neither one contradicts Einstein. This is worth pausing on because it may be the single most important idea in this entire video. Alcubierre did not find an exception to the speed limit. He found a way to satisfy it completely, while still producing the practical result of faster-than-light travel between 2 points. By changing the geometry of the space between those points, rather than the speed of anything moving through it. It is less like breaking a speed limit, more like discovering that the road itself can be folded. The paper, once published, spread quickly through the physics community, in part because of its almost cinematic implications, and in part because it was rigorous, technically sound general relativity, not speculation dressed up as science. Alcubierre himself, by his own account in later interviews, had been inspired partly by watching science fiction and wondering whether any version of faster-than-light travel could actually survive contact with real physics. Most attempts could not. This one, on paper, did. But even in Alcubierre's own original paper, one enormous caveat was present from the very first page. Creating this kind of distortion in space-time would require exotic matter, a category of material with properties unlike anything ever observed, held, or measured in a laboratory. The math worked. The geometry was valid. Einstein's equations permitted it completely. But permitting something mathematically and being able to build it are two very different claims, and the gap between those two claims is where the next part of this story lives. To understand why Alcubierre's proposal is taken so seriously by physicists, it helps to look closely at what life would actually be like inside that bubble, because the consequences are stranger and in some ways gentler than almost any other form of interstellar travel ever proposed. Every method of propulsion discussed so far in this video shares the same fundamental problem. To go faster, you accelerate, and acceleration, sustained over any meaningful stretch of time, is dangerous. Human bodies can tolerate roughly a sustained 3 to 4 times the force of gravity for extended periods before serious physiological strain begins, and far more than that only briefly, under controlled conditions, the way fighter pilots or astronauts train for short bursts. To reach even 10% of light speed using constant acceleration at a survivable rate, a spacecraft would need to accelerate for the better part of a year, and then decelerate for roughly the same duration, just to arrive at a stop rather than a catastrophic impact. The passengers, for that entire time, would feel the full physical weight of that acceleration pressing against them. The Alcubierre bubble sidesteps this problem entirely. And this is the part of the proposal that made physicists take it seriously rather than dismiss it outright. Because the ship inside the bubble is not itself accelerating, it is being carried by the expansion and contraction of space around it. The passengers inside would experience no acceleration at all, no g-force, no sense of motion whatsoever. From the perspective of someone standing inside the ship, the interior of the bubble would feel exactly like sitting still in a room, regardless of how fast the bubble itself was crossing the distance between stars. The mathematics places no upper limit on how fast the bubble itself could move, because the bubble is not an object subject to the mass wall discussed earlier in this video. It is a region of space-time geometry, and space-time geometry, as the galaxies beyond the Hubble volume already demonstrate, carries no such limit. There is a second, equally significant implication buried in the same mathematics. Time dilation, the effect that stretched and compressed time for anything approaching light speed through ordinary acceleration, would not apply to passengers inside an Alcubierre bubble, because they are never actually approaching light speed relative to their own local space. Their clocks, from their own perspective, would tick normally. A crew traveling to Proxima Centauri inside a bubble moving at 10 times light speed would experience the passage of time the same way anyone experiences an ordinary afternoon, arriving at their destination having aged only as many days as the ship's own clock recorded. Here's what that adds up to. If this could actually be built, it would solve nearly every problem raised so far in this video simultaneously. No dangerous acceleration, no relativistic time dilation for the crew, no infinite energy requirement from pushing an object's mass toward the light barrier, because the ship's mass, as far as the bubble is concerned, is never being accelerated at all. It is simply along for the ride. This is precisely why the paper spread through the physics community as quickly as it did after its 1994 publication. It was not a workaround or a technicality. It was, on paper, close to the cleanest possible solution to interstellar travel that general relativity could offer. But the phrase "on paper" is carrying a tremendous amount of weight in that sentence, and it deserves to be examined honestly rather than glossed over. A valid mathematical solution to Einstein's equations is not automatically a solution the universe is willing to permit in practice. General relativity is extraordinarily permissive about what shape space-time is allowed to take, mathematically. But the universe has other rules, rules about what kind of matter and energy actually exist, that narrow the field considerably. The question that follows the Alcubierre paper, and the question that occupied physicists for the 3 decades since, is not whether the geometry works. It does. The question is whether anything in this universe, or any universe, could actually generate that geometry in the first place. And to understand why that question turned out to be so difficult to answer, it helps to see how the physics community itself responded when the paper first landed. The reaction reveals almost as much about the size of the problem as the mathematics does. Inside a modest office at NASA's Johnson Space Center in Houston, a small team was doing something most people would have considered a waste of a government paycheck. They were trying to measure whether space itself could be bent, even slightly, on purpose, inside a laboratory. That team was led by Harold White, an aerospace engineer and physicist who, after earning his doctorate in physics from Rice University in 2008, went to work at NASA. There, White led a small research group, informally known as EagleWorks, formally titled the Advanced Propulsion Physics Laboratory. For most of the years following Alcubierre's 1994 publication, his paper existed almost entirely as a theoretical curiosity, discussed at physics conferences, cited in academic papers, occasionally mentioned in science journalism, but never seriously pursued as an engineering project. White decided to change that. In 2011, he published a paper titled Warp Field Mechanics 101, in which he took Alcubierre's original equations and reworked their geometry, attempting to reduce the staggering energy requirements the original proposal demanded. Picture what a room like this actually looks like, because it helps to abandon the image most people carry from science fiction. There was no chalkboard covered in equations under dramatic lighting, no single eureka moment. White's presentations, given at conferences including the 100-Year Starship Symposium, a NASA-affiliated event exploring the long-term feasibility of interstellar travel, were careful, methodical, hedged with the specific mathematical language of general relativity, delivered by a research group operating with a modest budget inside one of the more speculative corners of NASA's advanced propulsion research. This was not an announcement of a breakthrough. It was a working group, doing the unglamorous work of checking whether a mathematically elegant idea could survive contact with engineering reality. At EagleWorks, White's team built something called the White-Jude Warp Field Interferometer, a modified version of the same kind of instrument used in the 1887 Michelson-Morley experiment discussed earlier in this video, adapted to detect an extremely small, localized warping of spacetime, if one could be produced at all in laboratory conditions. The purpose was not to build a spacecraft. It was to detect the faintest possible signature of the effect Alcubierre's mathematics described. A signature so small that even a successful detection would represent nothing more than proof that the geometry could, in principle, be induced at all, at any scale. Here's the honest answer, stated plainly and without exaggeration. The results have been inconclusive. NASA's own public documentation on the Advanced Propulsion Physics Laboratory describes the warp field interferometry results this way, without claiming success and without ruling the concept out entirely. No warp bubble has been created. No space-time distortion has been conclusively measured. What the research did accomplish, however, was narrowing the theoretical problem. White's reworked geometry suggested that the energy requirements for a warp bubble, while still almost unimaginably large, might be significantly smaller than Alcubierre's original 1994 estimate. An important distinction that becomes central to the next part of this story. What this scene reveals, more than any single number or result, is how genuinely difficult it is to distinguish real, careful science from science fiction dressed in equations, and how the people who actually work on this question spend most of their careers holding both possibilities at once. Harold White has spent decades of serious, credentialed physics work chasing an idea that might, in the end, prove entirely impossible. That is not naivety. It is closer to a kind of professional patience most people rarely witness. The willingness to spend a career investigating a question whose answer might simply be no. But even a reworked, more efficient version of the Alcubierre metric still runs into the same wall that stopped the original 1994 proposal cold. And it is worth understanding exactly how large that wall actually is, in real terms, using real numbers, because the scale of it is difficult to overstate, and difficult, even now, to fully believe. The equations gave an answer. Physicists checked it twice, then a third time, hoping someone had made a mistake somewhere in the math. Nobody had. In his original 1994 paper, Alcubierre's equations implied that generating a warp bubble large enough to carry a spacecraft would require an amount of negative energy so large it defied ordinary comparison. Later analysis of the original geometry, carried out by other physicists studying the same equations, calculated that the negative energy required exceeded the total positive mass of the entire visible universe by 10 orders of magnitude, 10 billion times more energy than exists in every star, every planet, every galaxy, everything detectable across the observable cosmos, combined. This is not a large number in the ordinary sense. It is a number that exceeds the total energy budget of everything that exists. Picture being asked to boil a cup of water and being told the recipe requires more heat than every star in the universe has ever produced, combined, across the entire history of the cosmos. That is roughly the scale of the mismatch between what the original Alcubierre metric demanded and what the universe actually contains. This is not an exaggeration for dramatic effect. It is arithmetic, calculated directly from Einstein's own field equations, applied to the specific geometry Alcubierre proposed. For years, this energy requirement was treated as close to a death sentence for the entire concept. A theory that requires more energy than the universe contains is not a theory anyone can build toward, no matter how far technology advances. But in 1999, a physicist named Chris van den Broek, working at the Institute for Theoretical Physics at the Catholic University of Leuven in Belgium, published a paper in the same journal that had carried Alcubierre's original work, proposing a modification to the geometry of the warp bubble itself. Rather than changing the underlying principle, van den Broek adjusted the shape of the bubble, concentrating the region of negative energy into a much smaller, more efficient configuration, while still preserving a full-sized flat interior where a ship and its passengers could exist normally. The result was extraordinary. Van den Broek's revised geometry reduced the total negative energy requirement by 65 orders of magnitude. That is not a percentage reduction, and it is not even a 1,000-fold improvement. It is closer to the difference between the mass of the entire observable universe and the mass of a single grain of sand. Under Van den Broek's revised geometry, the total negative energy required dropped to the scale of grams, an amount that, in principle, is no longer cosmically absurd. Here's the strange part. The original number was not a soft, negotiable estimate. It was a hard mathematical consequence of the geometry Alcubierre chose, and yet, changing the geometry, while keeping the same underlying physics completely intact, transformed an impossible number into one that, while still far beyond current technology, at least belongs to the same universe we actually live in. This is precisely the kind of refinement Harold White was building on at Eagleworks, discussed in the previous section, when he reworked the metric further in his 2011 paper. But a smaller energy requirement is not the same as a solvable one, and reducing the number from impossible to merely extraordinarily difficult still leaves an enormous problem sitting at the center of the entire proposal. The energy, however much of it is ultimately required, has to be negative. Not simply hard to produce, not simply expensive, negative. A category of energy that behaves in ways ordinary matter and energy never do. And that category, as it turns out, poses a problem even stranger than the numbers themselves. The energy problem from the previous section carries a second, stranger requirement buried inside it, one that turns out to be even harder to satisfy than the raw quantity of energy involved. The Alcubierre metric, in every version studied so far, including Van den Broek's dramatically more efficient 1999 revision, requires negative energy. Not simply a very large amount of ordinary energy, but energy with a genuinely negative value. A category of physical substance that behaves in ways nothing in ordinary experience behaves. Here's what that would actually mean if you could hold some in your hand. Ordinary matter, everything you have ever touched, gravitates the way you would expect. It attracts other matter. It curves space-time inward, the way a heavy ball placed on a stretched sheet creates a dip that other objects roll toward. Negative energy would do the opposite. It would curve space-time outward, pushing rather than pulling, repelling rather than attracting. This is precisely the property Alcubierre's geometry requires to build the walls of the warp bubble, contracting space in front of the ship while expanding it behind. And ordinary matter, no matter how much of it you gather, simply cannot produce that effect. It has the wrong sign, built into its most basic physical nature. For decades, this requirement sat at the edge of pure theory, discussed mathematically, but with no evidence that negative energy existed anywhere in the real universe, in any amount, under any conditions. Then physicists returned to an experiment that had actually already confirmed it, decades earlier, in a completely different context. In 1948, a Dutch physicist named Hendrik Casimir, working at the Philips Research Laboratory in the Netherlands, predicted that two uncharged, perfectly flat metal plates, placed extremely close together in a vacuum, would experience a small attractive force, pulling them toward one another. The explanation involved quantum field theory, specifically the behavior of vacuum fluctuations, the tiny, constant flickering of particles and energy that quantum physics says exists even in empty space. Casimir showed that when two plates are placed close enough together, certain wavelengths of these fluctuations simply cannot fit in the narrow gap between them, while every wavelength remains available in the open space outside. The result is a measurable imbalance, a lower energy state between the plates than in ordinary vacuum, which is to say, in a very real, physically confirmed sense, a negative energy density. This prediction, unlike Alcubierre's warp geometry, has been directly measured. In 1996 and 1997, physicist Stephen Lamoureux carried out a precise experimental confirmation of the Casimir force, and his results matched Casimir's 1948 prediction to within about 5%. Since then, the Casimir effect has been measured repeatedly using increasingly sensitive equipment, and it remains one of the very few confirmed physical phenomena where negative energy density is not simply mathematically permitted, but actually physically present. Sitting in a laboratory between two ordinary metal plates, here's the softening turn, and where the excitement of that discovery meets the same wall, the energy angle already revealed. The negative energy density produced by the Casimir effect between two laboratory plates is astronomically small, occurring only across gaps measured in millionths of a meter, involving quantities of energy so tiny they can only be detected using some of the most sensitive force-measuring instruments ever built. Even Van den Broek's radically reduced warp bubble geometry, requiring negative energy on the order of grams rather than solar masses, would demand a concentration and scale of negative energy density that dwarfs anything the Casimir effect has ever produced, by many, many orders of magnitude. We have proven that negative energy is real. We have never come remotely close to producing enough of it, in a concentrated enough form, to build anything resembling a warp bubble wall. This is the shape of the problem that defines almost the entire modern warp drive research effort. Not whether negative energy exists, because it does, confirmed in a physics laboratory using equipment far less exotic than the phrase suggests. The problem is scale. A gap so enormous between what has been measured and what would be required that closing it may represent one of the largest engineering challenges ever proposed, if it can be closed at all. And exotic matter is not the only path physicists have explored toward faster-than-light travel. There is a second geometry, discovered even earlier than Alcubierre's, one that does not stretch space into a bubble, but instead punches a shortcut straight through it. The Alcubierre metric is not the only place in general relativity where Einstein's equations quietly permit something that sounds, at first, like fiction. There is a second geometry, discovered even earlier than the warp bubble, one that does not carry a ship along on a wave of expanding space, but instead proposes something more direct. A shortcut, a tunnel, connecting two distant points, allowing a traveler to step through one end and emerge somewhere else, without crossing the space in between at all. The mathematics behind this idea traces back to 1916, remarkably, just 1 year after Einstein published general relativity itself. A German physicist named Karl Schwarzschild found the first exact solution to Einstein's field equations, describing the spacetime around a single spherical mass, work that would later become foundational to our understanding of black holes. Shortly afterward, another physicist, Ludwig Flamm, examined that same solution and noticed something curious in its geometry. Mathematically, the solution seemed to describe not just a single region of curved space around a mass, but two regions, connected through a narrow throat. Flamm did not pursue the idea of the connection meaning anything physically. It sat, largely unexamined, for nearly 2 decades. Then, in 1935, Albert Einstein and a physicist named Nathan Rosen, working together at Princeton, published a paper titled The Particle Problem in the General Theory of Relativity. Their goal at the time had nothing to do with faster-than-light travel. They were attempting to describe elementary particles, like electrons, as smooth, non-singular features of space-time geometry itself, avoiding the mathematically troublesome infinities that appeared at the center of certain solutions to Einstein's equations. In pursuing that goal, they formalized the structure Flamm had noticed years earlier, describing physical space as two flat regions connected by a bridge, or throat. This structure became known as the Einstein-Rosen bridge, and it stands today as the historical ancestor of every wormhole concept that followed, including the ones now discussed in serious astrophysics papers and popular science alike. Here's something worth noticing about how this idea actually developed, because it complicates the neat, cinematic version of the story. The Einstein-Rosen bridge, as originally formulated in 1935, was not something a traveler could actually use. Later mathematical analysis, carried out by physicists John Wheeler and Robert Fuller in the 1950s, demonstrated that this particular bridge would pinch itself closed and collapse in a span of time too brief for anything, even a beam of light, to cross from one side to the other before the throat sealed shut. The original wormhole, discovered inside completely legitimate general relativity mathematics, was real in the sense that the geometry existed, useless in the sense that nothing could actually pass through it. That's the wormhole equivalent of Alcubierre's original energy problem. The geometry is valid, Einstein's equations permit it completely, and yet, in its natural, undisturbed form, the structure destroys itself too quickly to be of any practical use whatsoever. For decades, this seemed to close the door on wormholes, the same way the raw energy numbers seemed to close the door on warp bubbles. A wormhole existed, mathematically, but every wormhole anyone could describe using ordinary matter collapsed instantly. A beautiful equation with no working version anywhere in physical reality. But just as Van den Broek found a way to reshape Alcubierre's bubble into something with a survivable energy requirement, physicists eventually found a way to ask the same question about wormholes. If an ordinary, natural wormhole collapses too fast to use, could something be added to the geometry, deliberately, to hold the throat open long enough for a traveler to actually pass through? The answer, once again, involves the same strange substance that has haunted every version of this problem since it first appeared. And understanding exactly what that substance would have to do reveals why wormholes, despite being discovered decades before Alcubierre's warp bubble, remain just as far from a working technology today as the bubble itself. The story of how physicists arrived at a workable wormhole proposal begins in an unlikely place. Not a physics conference, a work of fiction. In 1985, the astronomer and science communicator Carl Sagan was finishing a novel called Contact, in which his protagonist would travel across an interstellar distance to reach a civilization near the star Vega. In his original draft, Sagan had written that journey as a plunge through a black hole. Wanting the science to hold up, he reached out to a friend, the Caltech physicist Kip Thorne, and asked whether that was actually plausible. Thorne's answer was no, and his reason was exactly the collapse problem introduced in the previous section. A black hole, mathematically related to the same Einstein-Rosen bridge structure discovered back in 1935, pinches its own throat shut far too quickly for anything, even light, to complete the crossing. If Sagan wanted his character to survive the trip, the physics needed a different kind of tunnel, one built specifically to remain open. This request turned into a serious piece of physics. Thorne, working with his colleague Michael Morris, spent the following months constructing a new mathematical model, formally published in 1988, describing a wormhole with a stable, traversable throat, held open long enough for a person to cross from one end to the other and back. Their paper, published in the American Journal of Physics, was framed partly as an academic exercise and partly as a genuine scientific question, and it asks something both simple and profound. If an ordinary wormhole collapses because gravity pulls its throat shut, what kind of substance would need to exist at that throat to push back against that collapse, holding the tunnel open by force? The answer Morris and Thorne arrived at was, once again, exotic matter. But this specific application reveals something new about what that phrase actually requires, beyond the negative energy density already discussed in the Casimir effect section. To hold a wormhole's throat open, the matter positioned there would need to exert what physicists describe as a negative pressure, a kind of tension pushing outward rather than compressing inward, strong enough to counteract gravity's natural tendency to collapse any open cavity in space-time. Ordinary matter, no matter how dense or how strong, always pulls inward under its own gravity. The substance required at a wormhole's throat would need to behave in the opposite direction entirely, a material with, in effect, a built-in resistance to being crushed that exceeds anything physics has ever measured in any naturally occurring form of matter. Notice something here. This is the same fundamental obstacle that stopped the Alcubierre warp bubble, appearing again in a completely different geometry. Two separate approaches to faster-than-light travel, developed independently, decades apart, using entirely different mathematical structures, both arrive at the identical wall. Neither the bubble nor the wormhole is impossible because the geometry is invalid. Both are mathematically sound, complete, internally consistent solutions to Einstein's equations. Both require a category of matter that has never been observed to exist in the quantities or configurations needed, anywhere, under any conditions humans have ever studied. This convergence is worth sitting with, because it is not a coincidence, and physicists studying both problems have noted as much. When two independently discovered paths toward the same destination both run into the identical obstacle, it suggests the obstacle may not be an accident of either particular geometry, but something closer to a structural feature of the universe itself, guarding against exactly this kind of shortcut. And if the geometry itself holds up, if both the bubble and the wormhole remain fully legal under Einstein's equations, then the next question becomes even stranger, and arguably more serious than the energy problem. If either of these shortcuts could somehow be built, what would they do to the order in which events happen? Because faster than light travel, it turns out, threatens something even more fundamental than energy conservation. It threatens the very idea of cause coming before effect. Everything discussed so far in this video treats faster than light travel as an engineering problem, a matter of energy, exotic matter, and geometry. But there is a deeper layer to this question, one that some physicists consider even more fundamental than the energy requirements already covered. It does not just ask whether FTL travel is difficult. It asks whether the very idea of it may be logically incompatible with the structure of cause and effect itself. To understand why, return to a concept introduced earlier in this video, Einstein's discovery that time is not absolute, that it can run differently for different observers depending on their relative motion. There is a related, equally strange consequence of special relativity called the relativity of simultaneity, and it states that two events happening in different locations, which one observer perceives as occurring at exactly the same moment, can be perceived by a different observer, moving relative to the first, as happening in a different order entirely. Not just appearing different because of the time it takes light to travel. Actually, mathematically, occurring in a different sequence, depending on the observer's frame of reference. For ordinary events, ones that unfold at normal speeds, this strange reordering never actually causes a problem, because the sequence of cause and effect, event A causing event B, remains consistent for every observer in every reference frame without exception. This is one of the deep, reassuring guarantees built into special relativity. No matter how you are moving, you will never observe an effect happening before its cause. Faster than light signals threaten to break that guarantee entirely. Einstein himself recognized this danger early, presenting a thought experiment in 1907, later refined with physicist Arnold Sommerfeld in 1910, describing it as a way to, in Einstein's own words, telegraph into the past. The modern version of this idea, formalized by physicists Gregory Benford, David Book, and William Newcomb in a 1970 paper, is known as the tachyonic antitelephone. The setup is straightforward. Imagine two observers, far apart, moving relative to each other. If the first observer could send a signal faster than light, and the second observer could send a reply back, also faster than light, then according to the mathematics of relativity, there exist valid reference frames in which the reply arrives before the original signal was ever sent. Not delayed, not confusing, genuinely, mathematically, backward in time, from the perspective of at least one valid observer. Picture receiving a letter today that responds to a question you have not yet decided to ask, a question you will only decide to send tomorrow. That is the shape of the paradox faster-than-light communication introduces into a universe governed by relativity. And crucially, this is not a hypothetical mathematical curiosity confined to a single, unusual thought experiment. Every wormhole and every warp bubble discussed earlier in this video, if they could actually transport matter or information faster than light between 2 points, would carry this same vulnerability built into their geometry, because the relativity of simultaneity is not a special exception. It is a fundamental feature of how relativity describes the relationship between space, time, and motion for every observer, everywhere. It's worth being honest here about where scientific consensus actually stands, because this is not a fully settled question. Some physicists treat the causality problem as the single strongest argument that faster-than-light travel must be forbidden by nature, regardless of whether the energy and exotic matter requirements could ever be solved. Others have proposed that the universe might simply prevent any actual paradox from forming through mechanisms still being explored theoretically, even if the raw mathematics of relativity appears to allow one. There is no unanimous answer, and honest physicists say so plainly. What is agreed upon across essentially the entire field is that any serious FTL proposal has to grapple with this problem directly. It is not a minor footnote. It may be the single deepest reason the universe seems so thoroughly determined to prevent this kind of travel, layered on top of the energy problem, layered on top of the exotic matter problem, each one independent, each one difficult enough to stop the effort on its own. And even if every one of these obstacles were somehow overcome, even if energy, exotic matter, and causality all found some resolution physicists have not yet discovered, there remains one more problem, quieter than the others, easy to overlook amid the drama of bending space-time. Whatever vehicle eventually attempts this journey will still need to carry something fragile, breathing, and entirely unsuited to the conditions of deep space. It will still need to carry a human being. Every problem discussed so far in this video concerns the physics of the journey itself. But even a perfectly solved warp bubble, a perfectly stabilized wormhole, a drive that somehow overcame every energy and causality obstacle already covered, would still face one more constraint, quieter and more intimate than the others, because it has nothing to do with space-time geometry at all. It concerns the fragile, specific creature that would actually have to survive the trip. The evidence for this problem does not come from theoretical physics. It comes from direct, repeated, decades-long medical observation of real astronauts, and it began almost as soon as humans started spending extended time in space. In the mid-1970s, crew members aboard the American space station Skylab were the first to reveal a pattern that has been confirmed consistently in every long-duration mission since. In microgravity, the human body loses bone density at a rate of roughly 1 to 2% per month. This is not a minor statistical footnote. By comparison to the most common form of bone loss on Earth, severe osteoporosis in elderly patients, it is a rate roughly 10 times faster. A single 6-month stay aboard the International Space Station can cost an astronaut roughly as much bone density as a postmenopausal woman on Earth loses across an entire year. Picture your skeleton aging decades in the span of months, simply because it is no longer required to bear weight against gravity. That is, in essence, what is happening. Bone is a living tissue that constantly remodels itself in response to mechanical stress, and without gravity constantly pulling against it, the body begins dismantling bone mass it interprets as unnecessary. Some of this loss partially reverses after return to Earth. A significant portion does not, and researchers studying returning astronauts have described the process as something close to a decade of accelerated skeletal aging, layered onto the body in the span of a single mission. Bone is only one part of a longer list. Astronauts also experience significant muscle atrophy, particularly in the legs and back, muscles whose entire evolutionary purpose is fighting against gravity every waking moment on Earth. Without that constant resistance, some astronauts have documented losing up to 20% of quadriceps strength after only a few weeks in orbit, even while following mandatory daily exercise regimens using specialized resistance equipment aboard the space station. And beyond low Earth orbit, where the International Space Station still benefits from significant protection provided by Earth's magnetic field, a second threat becomes far more serious. Galactic cosmic rays and solar particle events, high-energy radiation from deep space that Earth's magnetosphere normally shields against. A journey to Mars, or further, would expose a crew to significantly higher cumulative radiation than anything experienced aboard the International Space Station, with documented risks including increased cancer probability and, in NASA's own ongoing research using laboratory models, measurable damage to bone and other tissue from radiation exposure alone, independent of the effects of microgravity itself. Here's what this adds up to. The human body evolved across hundreds of millions of years under the constant, unbroken presence of Earth's gravity and its protective magnetic field, is simply not built for the environment a truly long interstellar journey would demand. Even a mission using conventional propulsion, taking years or decades rather than centuries, would require solving serious, unresolved biological problems just to deliver a crew that arrives capable of walking, let alone founding a colony or piloting a return journey. NASA and other space agencies have proposed solutions, including centrifugal habitats that would simulate gravity through rotation, a concept discussed seriously in mission architecture studies for Mars and beyond, though no full-scale version has ever been built or tested with a human crew for the necessary duration. This is the quiet, unglamorous underside of every faster-than-light proposal covered so far in this video. Even if physics eventually permits the warp bubble or the wormhole, biology imposes its own separate deadline, indifferent to whatever breakthroughs occur in exotic matter research. And this raises an uncomfortable question that connects the propulsion problem to something even stranger, a question this video has carefully avoided until now, because it involves not just matter and energy, but the very small, very strange particles that seem to ignore distance entirely, without ever actually breaking a single rule of relativity. There is one more angle to this story, and it involves a phenomenon so strange that Einstein himself, late in his career, found it deeply unsettling, referring to it dismissively as spooky action at a distance. That phenomenon is quantum entanglement, and understanding both what it does, and just as importantly, what it does not do, brings this video's investigation of faster-than-light travel to its final, most surprising conclusion. Entanglement occurs when two particles, often photons, are created or interact in a way that links their properties together, no matter how far apart they later travel. Measure a property of one particle, its polarization, its spin, and the corresponding property of its distant partner becomes instantly determined, correlated in a way that classical physics, the physics of everyday objects, cannot explain. This correlation appears to happen instantaneously, regardless of the distance separating the two particles, whether they are sitting a few feet apart in a laboratory or, in principle, on opposite sides of a galaxy. For decades, this was a subject of genuine, serious dispute among physicists. Einstein, along with colleagues Boris Podolsky and Nathan Rosen, argued in a famous 1935 paper that this apparent instantaneous connection suggested quantum mechanics was incomplete, that some hidden, unmeasured property must already determine the outcome in advance, preserving a more comfortable, classical picture of reality. In the 1960s, physicist John Stuart Bell developed a mathematical test, now called a Bell inequality, capable of distinguishing between Einstein's hidden variable explanation and the genuinely strange predictions of standard quantum mechanics. The experimental answer came in stages, and it did not favor Einstein. In 1982, physicist Alain Aspect, working with colleagues at the Université Paris-Sud in Orsay, France, conducted a landmark experiment using entangled photons, closing a significant loophole in earlier tests by switching measurement settings while the photons were already in flight, ensuring no ordinary signal could have coordinated the results in advance. The Bell inequality was violated, exactly as standard quantum mechanics predicted, and Einstein's hidden variable explanation was ruled out. Decades later, in 2022, Aspect, along with physicists John Clauser and Anton Zeilinger, received the Nobel Prize in Physics for this body of work, officially recognizing what had by then become one of the most rigorously confirmed phenomena in modern physics. Entanglement is real. The correlation is real. It has been tested, refined, and confirmed repeatedly, using increasingly sophisticated experiments that have closed nearly every conceivable loophole. Here's the strange part, and it's also the point where popular science most often gets the story wrong, which matters enormously for a question as central as this video's. Entanglement does not allow faster-than-light communication. This is not a minor caveat. It is a fundamental, mathematically proven limitation known as the no communication theorem, and it holds regardless of how instantaneous the underlying correlation appears to be. The reason is subtle but important. When you measure your particle and get a result, that result is genuinely random from your own local perspective. You cannot choose what outcome you get, and therefore, you cannot use your measurement to send a deliberate, chosen message to your distant partner. The correlation only becomes meaningful, only reveals its strange, coordinated pattern when the two separated observers eventually compare their results using an ordinary, conventional channel, radio, telephone, mail, something that travels at or below the speed of light. Until that comparison happens, each observer's individual results look like nothing more than random noise. Entanglement is real, confirmed, Nobel Prize-winning physics, and it does hint at a connection between distant particles that seems to ignore the constraints of ordinary space. But it cannot carry information, cannot send a message, cannot be used as a communication device, faster than light or otherwise. It is a correlation without content, a connection without a message riding along inside it. Even the strangest, most rigorously tested phenomenon in modern physics, one that briefly seemed like it might finally offer a genuine loophole around Einstein's speed limit, turns out, on close mathematical examination, to offer no exception at all. And so, after distance, propulsion, energy, exotic matter, wormholes, causality, biology, and now quantum entanglement, each angle examined carefully, each grounded in real, tested physics, the same conclusion keeps reappearing from every possible direction. It's worth pausing here, not to introduce one more angle, but to sit with the person actually listening to all of this, and ask what a number this large, examined from every possible direction, actually means for someone living an ordinary human life, on an ordinary human timescale, looking up at a sky full of stars that may simply be beyond reach. Take a moment to step back from the physics itself, because everything covered in this video, every equation, every experiment, every historical figure, ultimately points toward a single, very personal question. Given everything just described, given the mass wall, the exotic matter problem, the causality paradox, and the frailty of the human body itself, what does any of this actually mean for you? A person alive right now, looking up at a sky full of stars you will very likely never visit. Picture your own lifetime as a unit of measurement. A human life, on average, spans somewhere around 80 years if you are fortunate. In that span, you will witness roughly 29,000 sunrises. You will, if you are the sort of person drawn to a video like this one, spend some portion of those years looking upward, wondering what lies beyond the handful of points of light visible from your backyard. Against that backdrop, the numbers explored throughout this video take on a different weight. 73,000 years for Voyager 1 to reach the nearest star is not simply a large number. It is roughly 900 human lifetimes, laid end to end, one after another, just to cross the smallest possible gap between us and anywhere else. But there is a more hopeful number sitting quietly beneath all of this. One this video has not yet fully explored, because it does not require warp bubbles or wormholes or any physics beyond what we already understand. In the 1970s, a group of scientists and engineers at the British Interplanetary Society in the United Kingdom, led by a former Rolls-Royce rocket engineer named Alan Bond, undertook a 5-year engineering study called Project Daedalus. Their goal was strict and deliberately unglamorous: design an interstellar probe using only existing or near-future technology, nothing speculative, nothing requiring new physics, capable of reaching another star system within a single human lifetime. The design they produced was a 2-stage spacecraft powered by nuclear fusion, using a form of propulsion related to an earlier concept called Project Orion, first proposed by physicist Stanislaw Ulam in 1947. The Daedalus design would accelerate for nearly 4 years, its first stage burning for 2 years to reach just over 7% of light speed, before a second stage fired for close to 2 more years, pushing the final cruise velocity to roughly 12% of the speed of light. At that speed, the probe could reach Barnard's star, a red dwarf about 5.9 light-years away, within approximately 50 years. Well within a human lifetime, using only propulsion technology considered plausible using physics we already understand. Here's what the honest, unglamorous version of interstellar travel actually looks like, absent any breakthrough in warp geometry or exotic matter. Not decades to the nearest star, not centuries, something closer to half a century, achievable, at least on paper, using engineering principles that do not require inventing anything new about the laws of physics. Applied to Proxima Centauri specifically, a spacecraft cruising at 20% of light speed, a modest additional improvement over the Daedalus design, could complete the journey in roughly 21 years. a span well within the working career of the people who might launch it. This is where the idea of a generation ship enters the conversation. A spacecraft designed not to carry the same crew from departure to arrival, but to support an ongoing, self-sustaining human population across a journey lasting decades or, for more distant targets, centuries. The people who eventually arrive would not be the ones who left. They would be their descendants, born, raised, and living out entire lives aboard a ship in transit, inheriting a mission they never personally chose to begin. None of this requires solving the exotic matter problem. None of it requires resolving the causality paradox. It requires patience, engineering refinement, and an enormous, multi-generational commitment that no civilization has yet attempted. It is slower, humbler, and far less cinematic than a warp bubble. And it is, as far as current physics can tell us with any confidence, actually possible. The question this video leaves you with, then, is not simply whether faster than light travel will ever be achieved. It is whether the slow path, the 50-year probe, the multi-generational voyage, might be the only real answer humanity ever gets, and whether that answer, quietly, might be enough. Look back across everything covered so far in this video, and a pattern starts to emerge. One that is easy to miss when each obstacle is examined on its own, but impossible to miss once they are laid side by side. This was never really about a single wall. It was about a sequence of walls, each one independent, each one grounded in a different area of physics, and each one, on its own, sufficient to stop faster than light travel completely. Here's the shape of it. The energy required for even Van den Broek's dramatically reduced warp bubble geometry remains far beyond anything currently achievable. The exotic matter needed to fill that bubble, or to hold a wormhole's throat open, has never been observed in the necessary quantity or configuration, despite the Casimir effect proving that negative energy density is, at least in principle, physically real. The causality problem suggests that even if the first two obstacles were somehow overcome, the resulting technology might violate the basic ordering of cause and effect that the entire universe appears to depend on. And even setting all of that aside entirely, the human body itself, the fragile, gravity-dependent creature that would actually have to make the journey, begins deteriorating in ways modern medicine still cannot fully prevent, the moment it leaves Earth's gravity behind for any extended length of time. Faster than light travel is not blocked by a single simple prohibition, one equation standing guard at the border of what is possible. It is blocked by what feels, on reflection, closer to a conspiracy of independent constraints, each one arriving from a completely different branch of physics, each one discovered separately, by separate researchers working decades apart, and yet all of them, without exception, pointing in the same direction, toward no. That's genuinely strange, in a way that goes beyond simple difficulty. If there were only one obstacle, the energy requirement, say, then a single breakthrough might resolve the entire question. Find a more efficient geometry, discover a new energy source, and the door swings open. But when 4 or 5 separate obstacles all arrive at the same conclusion, independently, using entirely different mathematics, it starts to feel less like a coincidence and more like something closer to a message, as though the deep structure of physics itself has been built, quietly, deliberately, to prevent exactly this kind of shortcut, layering barrier upon barrier, so that even if one is somehow solved, another is already waiting behind it. Some physicists have speculated, informally, that this layered resistance might be the universe's way of protecting something more fundamental than mere travel: the integrity of cause and effect, the stability of the causal order that everything else, chemistry, biology, memory, meaning, ultimately depends upon. If effects could precede their causes even occasionally, even under rare, exotic conditions engineered by an advanced civilization, the consequences might ripple outward in ways far stranger and far more destabilizing than a simple engineering failure. It is possible, though far from certain, that the universe simply cannot afford to allow it and has built its physics accordingly. But this is speculation, offered honestly as speculation, not as settled fact. The truthful answer, the one that respects both the depth of the search and the limits of current knowledge, is that no one yet knows for certain whether this layered resistance is a fundamental, permanent feature of reality, or whether it simply reflects the boundaries of what one particular civilization, at one particular point in its scientific development, has managed to figure out so far. And history, when examined honestly, offers a quiet, persistent reason not to close the book too early on that second possibility. There is a word that has appeared throughout this video, applied to nearly every obstacle described: impossible. It's worth pausing on that word specifically near the end of this journey through the physics, because it has a complicated history, one that deserves to be told carefully, without overstating what it actually proves. For years before 1947, many aviation engineers genuinely believed that an aircraft attempting to fly faster than the speed of sound would be torn apart by the forces involved, a phenomenon they called transonic drag rise. The sound barrier, as it came to be known, was treated by some as a hard physical limit, not simply a difficult engineering target. Then, on October 14, 1947, an Air Force test pilot named Chuck Yeager climbed into a rocket-powered aircraft called the Bell X-1, was released from the belly of a modified B-29 bomber at high altitude over the Mojave Desert, and flew faster than sound, reaching just over 800 miles per hour at 43,000 feet. The barrier, once treated as an article of near-certain belief, turned out to be an engineering problem, not a fundamental law of nature. Better aerodynamics, a stronger airframe, and sufficient thrust were enough. It would be tempting to draw a straight line from that story to this one, to suggest that the light speed barrier, like the sound barrier, might simply be waiting for the right engineering breakthrough to fall. But that comparison, left unexamined, would not be honest, and this video has tried, throughout, to hold itself to a higher standard than that. The sound barrier was never written into the fundamental mathematics of the universe. It was a property of air, of pressure waves, of the specific physical medium sound happens to travel through. Change the medium, and the barrier changes with it. Sound moves differently through water than through air, differently still through steel. There was never anything cosmic about it. The light speed barrier is different in kind, not simply in degree. It emerges directly from the geometry of space-time itself, confirmed by over a century of experiments, from the Michelson-Morley result in 1887 to the particle accelerator results discussed earlier in this video, each one returning the identical answer, without exception, across every scale physicists have ever tested. It is not a property of some medium that light happens to travel through. It is built into the relationship between space, time, energy, and mass. The same relationship responsible for time dilation, for the mass increase discussed earlier, for the entire architecture of general and special relativity. There is no equivalent of switching mediums here. No alternate substance to travel through that might carry a different speed limit. And yet, holding that distinction honestly does not mean the door is fully closed, because this video has also shown, carefully, angle by angle, that the light speed barrier is not quite the single, simple wall it first appears to be either. Space itself, as demonstrated by the galaxies beyond the Hubble volume, carries no such limit. The Alcubierre metric and the traversable wormhole both remain mathematically valid solutions within Einstein's own equations, more than 30 years of careful research later. What stands between the mathematics and a working technology is not a broken law of physics. It is an engineering and materials problem of a scale humanity has never before attempted to solve, involving forms of matter we have only barely begun to detect, in laboratory quantities far too small to be useful. Whether that gap closes the way the sound barrier's gap closed, through decades of patient, incremental engineering, or whether it remains permanently unbridgeable, layered too deep in the causal structure of reality itself, is a question this video cannot answer with certainty. Neither can anyone else, honestly, today. What can be said, plainly, is that the search itself has already produced real, rigorously tested physics, real Nobel Prizes, real experimental confirmations, regardless of where the ultimate answer eventually lands. And that leaves us exactly where the most honest science always eventually leaves us, not with a final verdict, with an open question carried forward into the dark, waiting for whoever picks it up next. So where does this actually leave things after everything this video has walked through together? The distance itself, measured in trillions of miles, folded into numbers the mind was never quite built to hold. The mass wall, rising toward infinity as anything with weight approaches the one speed it can never quite reach. The loophole hidden in Einstein's own equations, the quiet distinction between moving through space and space itself moving, a distinction confirmed every single day by galaxies receding faster than light at the farthest edges of everything we can see. The warp bubble, mathematically sound, physically unbuilt. The wormhole, the same. The causality problem, waiting patiently behind both of them, older even than the mathematics used to describe it, dating back to a thought Einstein himself once had, in 1907, about what it might mean to telegraph into the past. And beneath all of it, quietly, the human body, aging in ways medicine still cannot fully arrest, the moment it leaves the gravity that shaped it. None of these threads has fully resolved. That is the honest shape of where modern physics currently stands, and it is worth resisting the urge, so common in stories like this one, to manufacture a tidier ending than the evidence actually supports. Research continues, quietly, in universities and laboratories scattered across the world, largely unnoticed by anyone outside the small community of physicists who spend their careers on precisely this kind of question. Refinements to the Alcubierre metric continue to appear in physics journals, each one attempting to push the energy requirement lower, the exotic matter requirement smaller, the geometry closer to something a future civilization, richer in understanding than our own, might actually be able to build. Wormhole stability calculations continue as well, exploring whether some configuration, some careful arrangement of negative energy might hold a throat open long enough and safely enough to matter. And beneath both lines of research, a deeper, slower project continues its own patient work. The search for a theory of quantum gravity, a framework that might someday unite general relativity with quantum mechanics. Two extraordinarily successful theories that still do not, even now, fully agree with each other at the smallest and largest scales of reality. Many physicists suspect that whatever answer finally emerges from that unification, whenever it arrives, may reshape this entire question in ways no one currently alive can fully anticipate. Perhaps that theory will close the door completely, revealing some final, unavoidable reason why nature simply will not permit this kind of shortcut, no matter how the mathematics is arranged. Perhaps it will open a door no one has even thought to look for yet, tucked somewhere in the deeper structure connecting gravity and quantum mechanics, invisible from where physics currently stands. No one knows. That uncertainty is not a failure of the research. It is simply the present, honest boundary of human knowledge, the exact place where careful science always eventually arrives, at the edge of what has been tested, looking outward into what has not. And so the search continues, unhurried, careful, spread across generations of scientists who will mostly never live to see its resolution, each one adding some small, verified piece to a puzzle none of them will finish alone. That, in the end, may be the truest thing this video can offer. Not a verdict, not a triumphant answer delivered with certainty, just the shape of an honest question, still open, still being asked, carried carefully forward by people who have chosen, for reasons that say something quietly hopeful about the species, to keep asking it anyway. To these words from somewhere on a small planet, orbiting an ordinary star, in an outer arm of a galaxy that is itself only one among hundreds of billions. Somewhere above you, whether you can see it right now or not, the same sky is turning that has turned for every person who has ever wondered the same thing you may be wondering. Whether the distance between here and anywhere else is truly as final as it feels. This video opened with a question. Have scientists found a real way to travel faster than light? And by now, the honest answer has revealed itself to be more interesting and more difficult than a simple yes or no. Einstein's equations do not forbid it outright. They forbid something narrower, motion through space beyond a certain speed, while leaving space itself free to move however it likes. Inside that narrow gap, physicists have found real, mathematically valid ways to imagine the impossible made possible. A bubble of contracted and expanded space, carrying a ship without ever making it move. A tunnel through the geometry of space-time itself, connecting two distant points without crossing the distance between them. Neither one has been built, neither one may ever be built, but neither one has been disproven either. And in physics, that distinction still matters. What remains after the equations and the numbers and the careful, honest weighing of every obstacle is something closer to a choice than a conclusion. A civilization can spend its centuries building slowly outward, generation ship by generation ship, 50 years to the nearest reachable stars, patient and certain and achievable with physics already understood. Or it can spend those same centuries chasing the harder, stranger possibility, refining the mathematics, searching for the exotic matter, waiting for the theory of quantum gravity that might finally settle the question either way. Most likely, if history is any guide, it will do some version of both at once, unwilling to fully commit to either patience or possibility. Somewhere in that unresolved space between what is achievable and what is merely imaginable, humanity keeps looking upward anyway. Not because the answer has arrived, because it has not, and because the not knowing, strangely, has never once been enough to stop the asking. The stars have not moved any closer tonight. They will not move any closer tomorrow. But somewhere, in a quiet office, or a laboratory, or the back of someone's notebook, the question is still being turned over, gently, the way it has been turned over for more than a century now, patient and unresolved and entirely, stubbornly alive.